Welcome back to The Explainer. So, today we're jumping into a fascinating piece of history. We're going to explore how two massive, explosive events back in the 16th and 17th centuries literally shattered humanity's understanding of an unchanging universe. Let's just dive right into the historical records and the modern science behind these absolute game changers. All right, imagine this for a second. You step outside right at noon, look up, and bam! There's a star you've never seen before, just blazing right there in the broad daylight next to the sun. Even today, that'd be wild. But for Renaissance astronomers, a sudden cosmic visitor like that was, well, deeply unsettling. It completely captivated them and, honestly, forever altered our entire cosmic paradigm. Section 1. Shattering the perfect cosmos. So before these explosions happened, people trusted this centuries-old belief system called Aristotelian cosmology. The core idea there was that everything beyond the moon was just perfect, immutable, totally unchanging. The stars were perfectly fixed. But then, this new Renaissance reality comes crashing in. Literally overnight, humanity went from believing in this perfectly undisturbed cosmos to witnessing these violent stellar catastrophes. It completely proved that the universe was capable of sudden, highly energetic change. Section 2. Tycho's Nova of 1572. The very first major crack in that perfect sky actually showed up in August 1572. There were a few early unconfirmed sightings, but the real turning point hits on November 11th. That's when astronomer Tycho Brahe starts meticulously documenting what he called a new star. And what makes Tycho's work so incredibly revolutionary is his math. His precise measurements definitively proved that this thing was way out there, at the immense distance of the fixed stars. It wasn't just, a nearby atmospheric trick or some weird weather anomaly. He actually tracked it for over a year until it finally faded from naked eye visibility around March 1574. To really wrap our heads around the sheer scale of this, we need to talk about its apparent magnitude, which peaked at -4. Now, in astronomy, the lower the number, the brighter the object. So hitting a -4 meant Tycho's nova was roughly as bright as the planet Venus. Think about that. It was shining with such exceptional brilliance that you could actually see it in broad daylight at its peak. I mean, the amount of energy required to do that from the distance of the background stars is just staggering. Section 3. Kepler's new star. Jump forward just a bit to October 1604, and boom, another brilliant new star pops up, this time in the constellation Ophiuchus. Now, he wasn't the very first person to spot it, but the legendary German astronomer Johannes Kepler became forever linked to this event. He went on to publish this massive, comprehensive treatise in 1606 called De Stella Nova in Pede Serpentari, basically on the new star in the foot of the serpent handler. And because his documentation was just so incredibly thorough, we literally still call it Kepler's supernova today. So this whole 18-month cosmic show kicks off in October 1604. It reaches a magnitude between -2.25 and -2.5, completely outshining Jupiter. And just like Tycho's nova, it absolutely dominated the daytime sky. But of course, then came the gradual fade. By January 1605, it dimmed down to equal the brightness of the star Antares. By October, it had dropped to 5th magnitude, and then finally, by the spring of 1606, it completely vanished from naked eye view. Back then, historical estimates about where this thing actually was were all over the place. But modern studies give us a much clearer picture today. This incredible daylight spectacle definitely did not happen in our solar system's backyard. Recent data actually puts it at about 16,300 light-years away from Earth, or roughly 5 kiloparsecs. Just let that sink in. The sheer scale of an explosion required to light up our daytime sky from 16,300 light-years away, it's honestly beyond comprehension. Section 4. Anatomy of Type 1a Supernovae. So, to figure out what kind of stellar monsters Tycho and Kepler were actually looking at, we have to fast forward to modern astrophysics and talk about something called the Chandrasekhar-Lemur limit. This is a very specific critical mass threshold of approximately 1.4 solar masses. Basically, it's the absolute maximum weight that a dead star, specifically a white dwarf, can handle before it becomes completely, fatally unstable. Today, modern analysis classifies both of these historical events as Type 1a supernova. It's a very specific, sequential kind of thermonuclear blast. Here's how it works. First, you have a dense white dwarf star in a binary system, and it's basically siphoning off and hoarding material from its companion star. It just keeps gorging itself until it hits that exact Chandrasekhar limit of 1.4 solar masses. And then, suddenly unable to support its own immense weight, the core just ignites. It triggers this massive runaway thermonuclear reaction. Now you might be wondering, how on earth do we know for sure this is exactly what happened over 400 years ago? Well, it's all in the physical evidence they left behind. When astronomers point their instruments at these specific explosion sites today, they find absolutely no surviving central star, like zero core left whatsoever. In visible light, all you see are these glowing, wispy filaments of surrounding nebulosity. It's the ultimate smoking gun, proving that the original white dwarf was just completely and utterly obliterated. Section 5. Modern Echoes in Space. Which brings us to a really fascinating question. How can we possibly analyze the exact thermonuclear reactions of an event that literally vanished from the sky in the early 1600s, way before the telescope was even a thing? I mean, the original visible light is long gone, right? Well, modern astronomers have some incredibly clever tricks up their sleeves for bypassing visible light entirely. First off, using radio and X-ray astronomy, they can track these super strong emissions radiating off the invisible remnants of Kepler's and Tycho's explosion sites. So even though our human eyes can't see the debris cloud, X-ray telescopes see it shining brilliantly. The second technique is light echo analysis, which is basically hunting for literal cosmic reflections of the original blast. And guys, this leads to an absolutely mind-blowing discovery. In 2008, scientists actually caught the original light from Tycho's 1572 explosion. How is that even possible? Basically, that ancient light had been traveling through space, bounced off a distant cloud of interstellar dust, and was perfectly redirected right back toward Earth. By analyzing this literal echo of light from the 16th century, scientists were able to officially confirm its Type 1a classification. That's over 4 centuries after Tycho Brahe first sketched it out in his notebook. It is, for all intents and purposes, natural time travel. So, these two exploding stars didn't just put on a crazy show in the daytime sky. They actually dismantled an ancient myth and helped lay the intellectual foundation for the entire scientific revolution. They proved beyond a shadow of a doubt that the universe is alive, it's volatile, and it's constantly changing. And it leaves you with this thought: if a single flash of light can completely shatter centuries of established belief, what other invisible cosmic phenomena are racing toward us right now, just waiting to rewrite our textbooks tomorrow?